Hi there, I welcome you to this course on physics of external beam radiotherapy. This is the first lecture in which I will give you a very basic introduction. This course has been designed for students mainly doing medical physics program, RTT program, and could also be useful for radiation oncologists who are interested in doing FRCR Part 1. So please give attention to these lectures. I hope it will be very useful. At the end of this lecture, I expect the student to be familiar with various radiation sources used in external beam radiotherapy, have understood the parameters such as SSD, SAD, isocenter, field size, penumbra, etc., and should be able to appreciate the concept of equivalent square and its use in dose calculation. There are several equipment that are used for external beam radiotherapy. Initially, it started with superficial X-rays, and then we had orthovoltage, otherwise called the deep X-ray therapy, that uses 300 kV X-rays. I put it as telecurie units because we had cesium as well as cobalt. Cobalt is still available, but cesium has been pensioned off. Then came in betatron, which could produce very high energy X-rays and electrons, linear accelerators, microtrons, and for proton and carbon ion we have the heavy particle accelerators. As we saw in the previous slide, superficial radiotherapy uses diagnostic quality X-rays. These are very low energies, approximately 50 to 150 kVp. Because of this low energy, it has got very low penetration. Therefore, it is used only for skin lesion, treatment of skin lesions, and treated with single beam. The maximum depth you can treat with this energy is about 5 millimeter. We use very small fields, and applicators are required to collimate the beam. You can see these applicators in this picture. There are two different types of applicators shown. One has got 15 centimeter focus to skin distance. The other one has got 25 centimeter focus to skin distance. These applicators are fixed onto this collimator, as you can see here in this picture. Superficial radiotherapy is not popular in India because we don't see many skin lesions. However, this is being used in several countries, including UK and countries in Europe, Canada and USA. It's still very popular there, but we don't use it in India. There are several issues with the superficial radiotherapy. Due to the short focus to skin distance, you get a very high output and large influence of inverse square law. Shorter the SSD, greater the inverse square law fall off, right? So there is a large influence of inverse square law. Calibration is difficult due to strong dose gradient, dose fall off, and electron contamination. Dose determined by the timer, so one has to take into account the on-off effects of the timer while calibrating. Photon beams may be contaminated with the electrons scattered from the applicator. That is another problem. The electrons may come off the applicator, which can give more dose to the patient surface. Next is orthovoltage unit. This is also referred to as deep X-ray therapy, DXRT. I remember calibrating this in CMC Velo way back in 86, but we don't use it anymore. Mostly the energy used is around 250 to 300 kVp. Treatment depths is around 20 millimeter, that is 2 centimeters. Some books say it can go up to 4 centimeters. Applicators are used again in this case as like the superficial X-ray therapy. Penetration sufficient for palliative treatment of bone lesions relatively close to the surface, that is to treat ribs, spinal cord, etc. There are few disadvantages of the deep X-ray therapy too. One of the interesting thing is higher dose to the bone. Deep X-ray therapy uses about 300 kV X-rays. At this energy, you have more of photoelectric interaction than Compton interaction. The photoelectric interaction, as you know, depends on the atomic number to the power 3. Since the bone's atomic number is much larger than of tissue, the dose to bone, absorption by bone, is much higher. This is okay if you are treating bone, But it is not okay if you are treating tissue, as bone would receive more dose than the tissue. So this is one of the major disadvantages of deep X-ray therapy. And maximum dose is on the surface. Therefore, one will get a higher skin dose. Treatment to a depth of only few centimeters possible. As we said, it can't go deeper. Low energy, hence high scattered radiation and larger penumbra. The penumbra is much larger. Very low energies when you go, you get a very high scattered radiation, and the penumbra, even though you have a point source of X-rays, the penumbra is much larger. The first telecobalt unit for treatment of cancer happened at the London Regional Cancer Centre, which is now called London Regional Cancer Program, London, Ontario in Canada on 27th October 1951. I worked in this institution during 2001 to 3, and they were celebrating 50 years when I joined this institution, 50 years of cobalt treatment. They were so excited about this cobalt machine. There were two centers. One is the London Regional Cancer Center in London, Ontario, and the other one was the Cancer Center in Saskatoon. They started with this cobalt machine. They called it cobalt bomb. This unit uses cobalt 60 radioisotope, which is produced from cobalt 59 by bombardment of neutron. So when neutron is bombarded on cobalt 59, a neutron capture happens and becomes cobalt 60, and during this process large energy is released, which is called the Q of the reaction. But this energy is not the one that is used for treatment, but this cobalt 60 is now radioactive because we have disturbed its N by P ratio by having a neutron into cobalt 59. Therefore, this cobalt 60 decays by emitting beta, that is, the neutron converts itself into a proton and a beta minus. So there are two beta minus particles that come out, one with 0.313 MeV energy, other one 1.486 MeV energy. But you can see that this beta 1 with 0.313 MeV energy has the maximum percentage, about 99.8%. And it takes to a little higher energy level, and then it comes to ground state by emitting two photons of energy 1.173 MeV and 1.33 MeV, and it becomes a stable nuclei of nickel. So these two photons of 1.17 MeV and 1.33 MeV are nearly equal in number, 99.8% and 100%. So we can take a mathematical average of it, and the average energy from cobalt is 1.25 MeV. The cobalt 60 machines nowadays can house cobalt source of 10,000 to 12,000 curie. The size of the cobalt source is approximately 1.5 centimeter to 2 centimeter in diameter capsule, and these machines have an SSD or SAD of 80 or 100 centimeters. You can have an 80 centimeter cobalt or an 100 centimeter cobalt. One of the advantages of going for 100 centimeter is you can have the shielding tray and other beam modifiers in, because of the larger distance between the diaphragm and the patient. But the disadvantages, when you go away, that is 100 centimeters, the output reduces significantly, right? So you have to increase the activity that you use to get a reasonable output. These are some of the models of cobalt unit over the years. This is a vertical unit. You cannot do isocentric treatment, but you can take it higher and even treat a larger field size with a larger SSD. This is called Eldorado A. Later on, it became Eldorado 8. One thing you can do is to do a swivel of the head to treat laterally. It is brought down and it is rotated to treat the lateral beam. But there is no isocentric treatment possible. Isocentric machines were first started with actually the Teratronic groups. They even had a 60 centimeter isocentric unit called a Teratron 60, which I have used in CMC Hospital Velo. And this is a isocentric unit provided by the Picker ATC C9. The C9 stands for 9000 curie. And this is Teratron 1000 with 100 centimeter SAD. And again, this can house up to 12,000 curie source. Betatron was one of the first electron accelerator used in radiotherapy. In India, a Betatron was installed at Christian Medical College Hospital, Vellore, India in 1978. This was a 42 MV Betatron. It provided 42 MV photon beams as well as 42 MeV electron beams. The advantage of using a Betatron, the only advantage probably, is a higher depth dose characteristics. By which I mean, if you have a 15 MV photon beams from Betatron and 15 MV photon beams from LINAC, the 15 MV photon beams of Betatron will have a better percentage depth dose. The disadvantage is it has got a very low beam output, that's a low dose rate. And it is a very massive structure. You need a lot of space, it's a huge installation. Then linear accelerator came into radiotherapy as electron accelerators, and actually it pushed off betatrons and it became the primary source of electron as well as X-ray beams. The maximum energy, though it could go for very high energy acceleration, in clinical use the maximum energy we have is about 23 MV. But the common energies used in radiotherapy are 6, 8, 10 and 15 MV photon beams, electron beams from 5 to 18 MeV. It gives higher beam output compared to Betatron. It gives higher dose rate but lower depth dose characteristics. If you noticed in the previous slides, I was mentioning about the unit of energy of X-rays and gamma rays as MV and MeV. I was using kV and MV for X-rays and MeV for gamma rays and for electrons. We need to know what is the actual unit of energy for X and gamma radiation and for electrons. The unit of energy is electron volt. When you say electron volt, what do you mean by that? How much is 1 electron volt? 1 electron volt is the energy gained by an electron when accelerated by a potential difference of 1 volt. That means when you give a potential difference between the anode and the cathode of 1 volt, the electrons are accelerated towards the anode and the energy gained during that process is called 1 electron volt. For example, if you are giving 1000 volts, the energy gained will be 1000 electron volts, or you can call it 1 kilo electron volt. So the energy of X and gamma radiation and electron radiation should be electron volts. But in actual practice, we don't use electron volts, we use kV/mV for X-rays, kV/meV for gamma rays as well as for electrons. Why is this difference? This is because the X-rays produced by Bremsstrahlung is a spectrum and not a single photon energy. It's not having one energy, it is having a spectrum. You can see in this graph, one uses 200 kV to produce X-rays. The X-ray produced will have various energies like about 10 kV and maximum number of photons in about 70 kV, and you also have some photons of 200 kV. So what energy would you use, which value would you use to talk about the energy of this particular X-rays produced by Bremsstrahlung? You cannot say 200 because there are energies which have 70 kV, there are energies which are 50 kV and etc. Therefore, it has become a common practice to talk about the voltage applied to produce the X-ray rather than the kV, because it's a spectrum, right? Therefore, you talk in terms of kV or MV, which means voltage of, for example, if you say 6 MV, it is like you are accelerating to 6 million volt, but the X-ray produced is a spectrum. So you are not using MeV, you are using MV. Let us go into the terminologies that we use in external beam therapy. Very common terminologies. One is source to skin distance, SSD. Some people say source to surface distance. Focus to skin distance, FSD, because in X-ray production, the source is actually a small point, it's a focal point. So people have the practice to say FSD rather than SSD. Then source to axis distance. The isocentric machines don't use the term SSD, they use a term SAD because it is the distance from the source to the axis point, like the axis of rotation point. Then you can also use focus to axis distance, FAD. The other terminology is isocenter, field size. It looks very simple, but I'll explain you. There is a small point there. Equivalent square and penumbra. What is SSD or FSD? As we discussed earlier, SSD is the acronym for source to skin distance. It is the distance between the source and the patient's skin. Alternatively, for LINAC or X-ray units, you can use the term FSD, which is the focus to skin distance. Machines have standard SSD. That means this is the point at which you measure the output or PDD, etc. For example, cesium units have 50 centimeters, cobalt have either 80 or 100, and linear accelerators do have 100 as the SSD. Why is it so important? Because the dose calibration for external beam unit, most of the time it is done at that SSD. Any change in this would change the dose by inverse square factor. And this becomes the reference for that machine, right? What is meant by SAD or FAD? It is the distance from the source to isocenter, that is the axis of rotation. It is 80 centimeter to 100 centimeter, 80 or 100 for cobalt units, and 100 centimeter for linear accelerator. You can get cobalt units with 80 centimeter SAD or 100 centimeter SAD. Linear accelerators have SAD, or we can call it FAD, of 100 centimeters. What is an isocenter? I did say that in the previous slide is the distance from the source to the axis of rotation, which is called the isocenter. Isocenter is the point in space where the axis of rotation of the gantry, couch, collimator and the beam central axis meet. So this, if you can look at this picture, this collimator can rotate in an axis. So there is an axis of rotation, which is also the beam central axis. The gantry can rotate about this axis. This is the axis of rotation of the gantry. The couch can rotate about this axis. This is the axis of rotation of the couch. And all of them meet at one point here, which is referred to as the isocenter. This is very important because for isocentric units, this point has to be identified in space accurately. What is the significance of this isocenter, or what is the advantage of this isocenter? You know that isocenter is the point at which the axis of couch rotation, gantry rotation, collimator rotation and the radiation beam central axis meet. Therefore, if you ensure accurate positioning of the patient tumor center at the isocenter, you can ensure accurate beam direction. If you position the center of the tumor at the isocenter of the unit, then whatever may be the angle of your gantry, couch or collimator, the radiation central axis will pass through the tumor central axis. So we will not have geographical miss. It has made a big change to the way we direct the beam onto the patient tumor. Earlier we used to struggle with the non-isocentric unit with beam directional devices such as pin and arc and back pointer, etc. When isocentric machines came up, the beam direction became very easy and more accurate. I have a small animation to show you the accurate beam direction in the case of isocentric units. As you can see here, let me say this is the tumor center and this is the central axis of the beam. As the gantry rotates from here to here, you can make sure that the central axis passes through the beam center throughout. So as you can see, but what is changing is the SSD. So the SAD is maintained constant, but the SSD keeps changing. So this is what we refer to the isocentric treatment, which was not possible when we had a vertical unit, as I showed, like Eldorado A or Eldorado 8. The next thing is field size. Field size is the width and length of the radiation beam at SSD or SAD. It's very important. When you say field size, you mean it is the width and length of the radiation beam at your reference point of SSD or SAD. And when you want to measure the field size in tissue or in water phantom, the field size is usually defined by 50% width of the profile or 50% isodose line. So this should correspond to the field size. For example, let me say you measured this profile with water phantom at, let me say, 80 centimeter or 100 centimeter, it's 6 MV X-ray, so 100 centimeter SSD, and you measured at 10 centimeter depth. So the field size at 100 centimeter SSD is 10 by 10, so at 10 centimeter depth it should be 11. So if you actually measure the 50 centimeter width of the beam, it will be 11 at this 11 centimeter at this point. So the field size in phantom is provided by 50% isodose line or 50% of the profile width. We can also say call it half width at full maximum. The other interesting thing we have to learn is the penumbra. Penumbra is the unsharp edge of the radiation beam created mainly by the finite source size. Penumbra could be classified into two. One is called the geometric penumbra, the other one is called the radiological penumbra. The geometric penumbra depends on source size, source to diaphragm distance, source to skin distance. Whereas the radiological penumbra consists of the geometric penumbra, transmission penumbra and the scatter. I will explain you what is geometric penumbra, what is transmission and what is due to the scatter. Let us first learn what is geometric penumbra. The diagram here explains you a geometric penumbra. In this diagram, S is the source size, P is the penumbra size at the depth D, C is the penumbra at the surface, source to surface distance is given by F, SSD is given by F, source to diaphragm distance SDD is given by FD. If you closely look at the two triangles, one formed by the source size, the other one by the penumbra, these two triangles, these two are similar triangles, meaning the ratio of the sides are equal, which means penumbra divided by source is equal to the distance from diaphragm to the penumbra level divided by source to diaphragm distance. Or I can say penumbra is equal to source into the distance from diaphragm to the penumbra level and divided by the distance from source to the diaphragm. So penumbra is equal to source size into this distance, which is SSD plus D, SSD plus D minus SDD, right? That is this distance divided by SDD, source to diaphragm distance. I can rewrite this equation as penumbra is equal to source size into SSD F plus D, that is the total depth, minus SDD, which is FD, divided by SDD, which is FD. Penumbra at the surface, CE, is simpler because you don't need to include this D. So the equation now reduces to source size into SSD minus SDD, F minus FD, divided by SDD, which is FD. Right? So you can get the penumbra using this equation. Now from this equation you can say penumbra will increase if the source size increases or SSD increases or the depth increases. Penumbra will decrease if source to diaphragm distance increases. That means if you bring the diaphragm closer to the patient, the penumbra will be much smaller. But there will be other problem. There will be scatter from the diaphragm to the patient, which will increase the skin dose. The other penumbra, which I said the transmission penumbra, if you look at this, if you see one of the rays at this edge of the source will trace the collimator, like the diaphragm, it will just go at the side of the diaphragm. It will just trace the same divergence of the diaphragm. Whereas the ray from the other edge of the source will go through little bit into the diaphragm. And there is an attenuation here. This will create a decrease in dose at this point compared to the dose at this point, apart from the distance issue. So this decrease due to this attenuation is called the transmission penumbra. The radiological penumbra includes lateral scatter. So the lateral scatter increases the radiation beam penumbra, otherwise called the radiological penumbra. More side scatter, larger penumbra. Density of scattering medium affects the penumbra. If you have a high density medium, there will be more scatter, more penumbra. Larger the penumbra, greater the dose to normal tissue. So you want to have a smaller penumbra. One good thing is smaller source size, like in the LINAC, reduces the size of the penumbra, right? But increase in SSD increases the size of the penumbra, right? Let us look at this one. Now, this is what we refer to as the penumbra inside the patient or inside the phantom, where the scatter increases the size of the penumbra much more. This is what I refer to as the geometrical penumbra, but it is much more than this due to the scatter that happens here. You can note that if you do it in the air, a beam profile or measure across the beam, it will be like this. But if you do it in phantom, you see the penumbra increases. So it was a very sharp edge here. The edge is not very sharp. It is quite, unsharp edge you get when you do it in the phantom at various depths. Right? How do you measure radiological penumbra? Radiological penumbra is measured as the width of 80% to 20% of the dose profile. What you have to do is to get the dose profile at the reference depth, maybe 10 centimeter or at Tmax, and look at where you get 80% with reference to the central axis and where you get 20% with reference to the central axis. And the distance between the 80% to 20% and this is referred to as the radiological penumbra. It is better to have a smaller radiological penumbra. Some of the points to remember with regard to penumbra. It increases with source size, we saw that earlier. Decreases with source to diaphragm distance. Increases with source to surface distance. And does it increase with beam quality? This is a question mark. We know that for lower beam quality like deep X-ray therapy, we had large penumbra. But when we went to cobalt, it was less but larger than 6 MV because of the source size. But as the beam quality increases, what happens? These are some of the penumbra measured by me with cobalt as well as 6 and 15 MV beams. You can look at for cobalt, I get about 12.8 mm. For 6 MV, I get 4.6 mm, but for higher energy, 5.43 mm. So with energy, here I see an increase in it. Did I make any mistake? Is it correct? Yes, it is correct. You will have an increase when you go to high energies. Why do you have that increase? Let us look at it. Here, I'm going to explain you the increase in penumbra for high energies with the help of isodose curves. You can look at the isodose curve for cobalt 60, that 10% isodose line width, if you look at, it is 13.8 centimeters. When you go to 6 MV photon beams, the isodose line, 10% isodose line width is 12.26 centimeters. And when you go to 15 MV photon beams, it is 12.6 centimeters. So there is an increase in the width of 10% isodose line as compared to 6 MV. This is because of the increase in the penumbra when you go to high energies. Why is the penumbra larger for 15 MV as compared to 6 MV? The reason is when photons interact, they set in motion Compton electrons. These Compton electrons carry an energy depending on the angle of scatter. Sometimes it could be as large as the incident photon energy. For example, a 15 MV would produce a Compton electron having a larger energy than a 6 MV. For example, if a Compton electron is set in motion somewhere here by a 15 MV photon, then that Compton electron will have a larger range and they will travel little longer distance compared to an electron set in motion by a 6 MV beam. So naturally, because of the larger electron track, 15 MV will have a larger penumbra compared to the 6 MV beam. Thank you very much. Please do the MCQs as usual. And if you have any questions, you can type in the comments. When time permits and if time permits, I will try to reply. Thank you very much.